Alright everyone, welcome back to the AI Research Roundup. I'm your host, Alex. Today is May 4th, 2025. We're diving into an interesting ICLR conference paper called Kinetix, investigating the training of general agents through open-ended physics-based control tasks, published just over 3 months ago, back in January. So this paper introduces Kinetix, basically an open-ended 2D physics playground designed to train general RL agents that can tackle brand new, unseen tasks. Okay, so this first figure really sets the stage. On the left, you see examples of the vast number of randomly generated physics tasks the agent trains on, millions of them, all looking quite different. Then, on the right, we see the test environments, things like Grasper, Pinball, Lunar Lander. These are human-designed, unseen tasks. Crucially, the goal is always the same: get the green shape to touch the blue, avoiding the red. Okay, so how does the agent actually see these tasks? This figure shows its transformer-based architecture. Instead of pixels, it gets symbolic info about each entity, shapes, joints, etc. It uses self-attention and message passing to figure out how they all relate, before deciding on actions via the final layers. This structure is key for handling the diverse, unseen tasks we saw earlier. Building on that architecture, this next figure shows how well that agent actually performs on those unseen, human-designed tasks we saw earlier without any extra training. We're looking at the zero-shot solve rate plotted against billions of training steps. You can clearly see performance improving dramatically, especially on the small and medium tasks. Much better than random guessing. This really highlights the agent's growing generalization capability as it trains. Okay, so we saw the agent has decent zero-shot ability, but what about fine-tuning it on specific tasks? Well, this figure compares the pre-trained agent, fine-tuned, that's orange, against training a specialist agent from scratch, blue, across all the large tasks on the left. Fine-tuning learns much faster, and look at the right, especially Mujoko Walker Hard. The fine-tuned agent solves it, while training from scratch completely fails. It really highlights the power of pre-training. Now, all that large-scale pre-training and fine-tuning we just discussed, it needs a lot of simulation steps. So this figure compares the speed of JAX 2D, the new engine they built, against the standard Box 2D. We're looking at steps per second versus parallel environments. You can see JAX 2D, that's the red line, scales much better, especially with RL training involved. This speed is absolutely essential for generating the billions of interactions needed. Right, so with billions of steps possible thanks to JAX 2D, how did the authors actually select the training tasks? This figure looks at that, comparing SFL, which uses learnability, that's the blue line, to standard domain randomization, DR, in orange. We see SFL generally achieves a higher zero-shot solve rate, particularly on the small and medium tasks. Both methods find the large tasks on the right much harder though. Okay, so building on that idea of task selection, this figure broadens the comparison. It plots the zero-shot solve rate again, but now comparing SFL, that's the red line, against other curriculum methods like PLR and ACEL alongside drive across both the medium and large tasks shown here. SFL consistently achieves the highest solve rate throughout most of the training. It really reinforces that selecting tasks based on learnability seems most effective. Alright, so wrapping things up, we've seen this agent, especially when trained using SFL on those diverse tasks, achieves pretty good zero-shot generalization. And, critically, fine-tuning it allows solving really challenging tasks, ones that fail completely when trained from scratch. It really shows this large-scale pre-training approach is quite promising for building general RL agents. That's it for today. Thanks for joining the AI Research Roundup.